Hello. Recall that in the previous lecture we introduced Tor, the onion router. We will now discuss its operation in detail. To discuss the operation of Tor in detail, we introduced some terminology. Recall that in Tor, a source connects with a destination through three intermediate relays. So an example is shown here. This is the source or the client, and this is the destination. And the connection between the source and the destination is via three intermediate relays. This is the first relay, this is the second relay, and this is the third relay. And the connection is shown here by these lines. So this is the connection from the source to the first relay, then from the first relay to the second relay, and so on. This is the connection from the second relay to the third relay, and this is the connection from the third relay to the destination. So the first relay on this path is known as the entry relay or the guard relay. This is the entry point to the Tor network. The Tor network is shown in the middle here. All these are Tor relays. But the three relays used in this particular connection are this one, and this one. The first of these relays is known as the entry or the guard relay. Then the next relay on the path, which is this one, is the middle relay. The middle relay is used to transport traffic from the guard relay to the exit relay. We will see that the exit relay is the third relay on the path. So this is the exit relay. Since the middle node is used to transport traffic from the guard relay to the exit relay, this prevents the guard and exit relays from knowing each other. So in this example, this relay does not know that it is communicating with this relay, because the middle relay relays traffic between these two relays. So hence, these two relays don't know that they are communicating with each other. Then the exit relay is the third relay on the path that is shown here. This exit relay sends traffic to the final destination intended by the client. So as we can see here, the exit relay communicates with the end destination. So this terminology will be used throughout this lecture. The first relay is the guard relay or the entry relay. The second relay is the middle relay, and the third relay on the path is the exit relay. Tor, as the name suggests, it uses what is known as onion routing. Recall that Tor allows independent individuals called volunteers to contribute relays to its relay pool. So some relays may be malicious. A particular individual who contributes a relay may want to actually compromise the anonymity of connections that are being conducted over Tor. So some relays may be malicious or mischievous. No individual relay should know as to which two parties are communicating. Hence the use of three relays as opposed to only one relay. So if only one relay were used instead of three relays, then if that relay were malicious, then it would know who is communicating with whom. And it could disclose this information to others. So hence the use of three relays, so that even if one of them is compromised, even if one of them is malicious, no one knows who is communicating with whom. No relay should be able to read the data that they are communicating. Tor is designed to put as little trust in relays as possible. So as we said, the use of at least three relays is precisely so that even if one of them is malicious, it cannot know who is communicating with whom, and hence it cannot leak this information. In particular, the design ensures that each relay on the path between Alice and Bob only knows which node gave it data and which node it is giving data to. So for example, this relay only knows the identity of this client and the identity of this relay, but it does not know the identity of this relay or the identity of the destination. No individual relay knows the complete path that a data packet has taken. Also, the entry and middle relays cannot read the data that is being sent from Alice to Bob. So this link is encrypted, this link is also encrypted, this link is encrypted, and as we saw earlier, this link is optionally encrypted. So if Alice and Bob use HTTP without TLS or any other encryption, even then the entry and middle relays cannot read the data that is being sent from Alice to Bob. The third relay knows the destination's IP address, that is Bob's IP address, but it does not know who is communicating with Bob. The third relay can read the data being exchanged with Bob if it is not encrypted, and it cannot read it if it is encrypted. For example, if TLS is used. So these properties are implemented using onion routing. When a client sends data over a connection through the Tor network, that connection is shown over here. So the encryption of the plaintext data generated by the source is shown over here. So this is the original data. So when a client sends data over a connection through the Tor network, it encrypts the original data, which includes the header, which contains the destination address, such that only the exit relay can decrypt it. So that encryption is shown here by the yellow layer. So this is the exit relay encryption. The original data plus the header, which contains the destination's IP address, this is encrypted using this exit relay encryption. So it is encrypted such that only the exit relay can decrypt it. Then after this exit relay encryption, the client adds the address of the exit relay to the encrypted data and then encrypts the result again such that only the middle relay can decrypt it. So that second encryption is shown over here. So this is the middle relay encryption. So after doing the exit relay encryption, the client adds the header, which includes the identity of the exit relay, to this information, and then it encrypts the resulting information, and that is the middle relay encryption. Then again the client adds the address of the middle relay to the encrypted data and encrypts the result once more such that only the guard relay can encrypt it. So this third encryption is shown here by the purple layer. Finally, the client sends this package to the guard relay. The client obviously knows the IP address of the guard relay. The client knows the IP addresses of all three relays as well as the destination. Hence the client can send this package to the guard relay. Now, when the guard relay receives this package, it decrypts the outer encryption, that is the purple encryption, and once it decrypts this, it gets the IP address of the middle relay. So recall that at this stage we had added the address of the middle relay to the encrypted data and then encrypted it once more so that only the guard relay can decrypt it. So hence when the guard relay decrypts this purple layer of encryption, it gets the IP address of the middle relay. So hence it can send the decrypted packet to the middle relay. So this purple layer and the inner layers, these are sent to the middle relay. Then the middle relay can decrypt this green layer of encryption, and once it decrypts it, it gets the IP address of the exit relay. So then the middle relay forwards that packet to the exit relay. Then the exit relay receives it and it decrypts this yellow layer of encryption, and then it extracts the original data and sends it to the destination. So notice that the original data is wrapped in layers of encryption like the layers of an onion, hence the name onion routing. So we can see that this is the first layer which is put onto it, then this is the second layer and this is the third layer. So these are like the layers of an onion, hence the name onion routing. By doing this, each relay only has the information it needs to know, which node it got the encrypted data from and which node it will send the data next to next. So note that exit relays can read the original data that is sent by the client because they have to pass that data to the destination. So if credentials are passed over HTTP, FTP or other plaintext protocols, then the exit relay can steal these credentials. So this can be defended against by ensuring that the data exchange between the client and the destination is performed using a secure protocol such as TLS. If TLS is used to encrypt the information, then even the exit relay is not able to read that information. Now there are some questions that need to be addressed in the operation of Tor. One question is, how is a circuit established from Alice to Bob via 3 relays? So the source Alice cannot simply send packets to the 3 relays directly, because the second relay should not know, that is the middle relay should not know the identity of Alice, and the exit relay or the third relay also should not know the identity of Alice. So it's challenging to establish a circuit from Alice to Bob via 3 relays. So how is such a circuit established? Note that each relay should only know the identities of the nodes before and after it in the circuit. Suppose Alice establishes a circuit to Bob via 3 relays. How is data sent from Bob to Alice? That is in the return path. So how does Bob know where to send the data to? So notice that Bob only knows the identity of the exit relay. Bob does not know the identities of the middle relay, guard relay, or of Alice. So how does Bob know how to send the information, the return information back to Alice? Note that Bob does not know Alice's IP address. However, encryption key is established between Alice and each relay. Again, we have this challenge that each relay should only know the identities of the nodes before and after it in the circuit. So we now discuss how these questions are addressed in Tor. So we consider a simplified version of Tor and discuss how these questions are addressed. So first we discuss circuit establishment and key establishment. That is, we will discuss how to address the first question. That is, how is the circuit established from Alice to Bob via 3 relays, and how to address the third question. That is, how are encryption keys established between Alice and each relay. Each relay has an RSA public key, public-private key pair and the corresponding certificate. There is a TLS connection between each pair of relays over which data can be encrypted and sent. Suppose Alice wants to establish a circuit with Bob via the relays R1, R2, and R3. Note that Alice cannot directly communicate with R2 or R3 because they should not know the identity of Alice. So Alice can only directly communicate with R1. If Alice wants to send a message to R2, then it should be via the relay R1. Alice first sends a request to R1 to create a connection with it. A TLS connection is established between Alice and R1. So let's illustrate that. This is Alice, and first a connection is created between Alice and R1. So this is a TLS connection between Alice and R1. Symmetric keys for encryption are agreed upon between Alice and R1 using the usual procedure in TLS. So using that procedure, symmetric keys for encryption are agreed upon between Alice and R1. So Alice can now send encrypted data to R1. Subsequently, all communication between Alice and R1 is encrypted. Now an ID, say A, R1 is assigned to the connection between Alice and R1. So this connection is assigned an ID. Let's call it A, R1. So A, R1 is the identity of this connection. Then in the next step, Alice sends a request to R1 over this established connection, specifying the address of the next relay, which is R2, and requesting for the circuit to be extended to R2. Alice sends a request to R1 requesting that the circuit be extended to the next relay, that is R2, and Alice specifies the address of R2 to R1. That way R1 knows that it should establish a connection with R2. So Alice informs the address of R2 to R1, and then R1 establishes a connection with R2. R1 sets up a connection with R2 and assigns an ID, say R1, R2, to the connection between R1 and R2. Note that R1 does not reveal the identity of Alice to R2. So let's label this connection between R1 and R2 by this identifier R1, R2. So this is the identifier of the connection between R1 and R2. R1 maintains an association between these IDs A, R1 and R1, R2 on the incoming and outgoing connections respectively. So that way R1 knows that any information that is received over the connection with ID A, R1 should be forwarded on the connection with ID R1, R2, and conversely any data that is coming on the return path from this connection with ID R1, R2 should be sent on this connection with identifier A, R1. So that's the advantage of maintaining an association between these IDs A, R1 and R1, R2 on the incoming and outgoing connections. Then LS selects symmetric keys for encryption, encrypts them using R2's public key and sends them to R2 via R1. Thus, symmetric keys are established between LS and R2. So LS selects some random symmetric keys which will be used for securely communicating with R2. Then LS sends these encrypted keys to R1. Then R1 forwards them over this connection to R2. So at this point, symmetric keys have been established between LS and R2. So LS can send encrypted data to R2 and vice versa. R2 can send encrypted data to LS. In this manner, the circuit is extended hop by hop to R3, and then symmetric keys are agreed upon between LS and R3. So this connection is extended to R3. An identifier is assigned to this connection. This identifier is R2, R3. And finally, from R3, the connection is extended to Bob. And this connection is assigned the ID R3, Bob. So each relay knows the identities of only the nodes before and after it on the circuit. R3 sets up a connection with Bob. That connection is shown over here. Assigns an ID to it, say R3, Bob, and maintains an association between the IDs R2, R3 and R3, Bob. So this shows the establishment. So overall, in this process, a connection has been established between LS and Bob, but this has the feature that each relay only knows the identities of the relays before and after it on the path. Now we have answered the first and third questions, namely, so in the questions that we raised, we have answered the first question, how is the circuit established from LS to Bob via 3 relays, and we have answered the third question, how are encryption keys established between LS and each relay. Now we answer the second question, how is data sent from Bob to LS on the return path. So suppose LS has established a circuit to Bob via 3 relays R1, R2 and R3 as we discussed on the previous slide. So how is data sent from Bob to LS? So to send data, we make use of the identifiers that we have assigned to different connections. Note that Bob does not know LS's IP address. Bob sends data over the connection with ID R3, Bob to R3. So in the previous picture, Bob knows about this connection between itself and R3. So Bob sends the data over this connection with identifier R3, B. Now R3 knows that the ID R3, Bob corresponds to the ID R2, R3. So R3 forwards the data to R2 over the connection with ID R2, R3 and so on until the data reaches LS. So in this picture, R3 maintains an association between the connection with ID R3, Bob and the connection with ID R2, R3. So whatever data it receives from Bob, it forwards that data over this connection with ID R2, R3. Similarly, R2 has maintained an association between the connection with ID R2, R3 and the connection with ID R1, R2. Whatever data it receives from the connection with ID R2, R3, it forwards on the connection with ID R1, R2 and so on and so forth. So this way the data finally reaches LS. So we have answered the second question as well. How is data sent from Bob to LS? Now, how should data be encrypted as it travels on the path R3, R2, R1 to LS? So the data is encrypted in the same way as the data sent in the forward direction from LS to R3 with 3 layers. But in this case, the layers of encryption are added one by one, like an onion having its peels put back on. One layer is added by R3, R2 and R1. So it is an exercise for you to think about this and find out why these layers of encryption are added one by one. So at a high level, these are added to protect the identity of R3 from R1 and the identity of R3 also from R1. So these layers of encryption are added so that R1 does not know the identity of R3. So the message that is sent by R3 is encrypted by R2 so that R1 does not know R3's identity. It's an exercise for you to think about how adding these layers of encryption one by one by R3, R2 and R1 achieves anonymity. So we have discussed the operation of Tor in detail. Now we discuss the limitations of Tor. So Tor does not provide protection against end-to-end timing attacks. So some attackers spy on multiple parts of the internet and they use sophisticated statistical techniques to track the communications patterns of many different organizations and individuals. For example, consider an attacker who can watch the traffic coming out of Alice's computer. This is the internet, and Alice is connected to the internet by a certain connection, and this is the connection from Bob's computer to the internet. So an attacker watches the traffic in different parts of the internet, and in particular the attacker watches the traffic coming out of Alice's computer. The attacker also watches the traffic arriving at her chosen destination, say Bob's computer. So the attacker also monitors the traffic that is flowing on this connection between the internet and Bob. Then the attacker can use statistical analysis to discover that they are parts of the same circuit. Consider the sequence of packets that are being sent from Alice into the internet and the sequence of packets that are being sent from the internet into Bob's computer. So these are statistically similar. For example, the spacings between adjacent packets and the lengths of different packets which are sent on this connection are similar to the spacings between different packets and the lengths of different packets that are sent on this connection. So whatever packets are sent from Alice, after some delay, similar packets are sent from the internet to Bob. So by observing such correlations, an attacker can find out that these packets are part of the same connection. So that way an attacker can use such end-to-end timing attacks to find out who is communicating with whom. So these techniques are challenging and they require the attacker to monitor different parts of the internet. So the monitoring cost is extremely high, but if the attacker has so many resources, then it can launch such an attack, an end-to-end timing attack. Another limitation of Tor is that if a user Alice does not want to reveal her identity to the destination Bob, in that case she needs to ensure that the data she sends to the destination does not contain any information that reveals her identity. For example, she should not type her name or address in web forms or send any information that reveals her computer's configuration. So Alice has to be careful in this respect. So if she types her name or address in web forms or sends any information that reveals her computer's configuration, then the anonymity is compromised. So that should not happen. Hence, Alice has to be careful while communicating with Bob. These are some limitations of Tor. So in summary, we discussed the operation of Tor. We discussed that a source Alice communicates with a destination Bob via 3 intermediate relays, and we discussed how a circuit is established from Alice to the destination Bob via 3 intermediate relays, and how are symmetric keys established between Alice and each relay. And we finally also discussed how Bob sends information back to Alice despite not knowing Alice's ID. So we discussed how data can be sent on the return path. And finally, we discussed the limitations of Tor. So this concludes our discussion of anonymous connections and onion routing. Thank you.